Hello and welcome. The topic of today's presentation is autoregressive flows for density estimation. So let's quickly overview what normalizing flows are. A normalizing flow defines a series of invertible transformations that take a known latent variable z0 and transform it into the target density. Usually the choice of transformations in a flow comes down to reducing the complexity of computing the determinant. One of the first flows that I looked at was called planar flow, which was introduced in one of the papers that I did. Here we take f of z and we use the weights and a bias term and a scale term. And in principle, if you develop enough of these flows, you can target any arbitrarily complex density. In my implementation that I find that if we work with few flow lengths, say for instance 2 in the case on the right, we see the same problem that is observed as the mode collapse problem in GANs. And basically this can be remedied by increasing the number of flows. And we see on the bottom the one with 16 flows. So this bottleneck property is because there is a single nonlinearity in planar flows, and this can be remedied by increasing the size of the weights and the bias terms. So now we move on to autoregressive flows. So the autoregressive property basically just says that you can break up a probability distribution and condition on the previous x minus 1 terms. So if we now take so basically the output of the ith node depends on the previous I minus 1 nodes. So we can scale the zth input by this exponential e to the sigma plus this mean term, where these sigma and mu are functions of x minus 1 previous inputs. And basically in practice, f and g are fully connected neural networks. Now, in the math paper, the way they achieve the autoregressive property is by creating masks. So you take a fully connected network and you develop masks for each layer. And what the masks do is that they turn on or turn off certain nodes, and based on that, we can achieve the autoregressive property. This single unit is called a made unit. It was first realized in the made paper, and this helps parallelize the operation. So what I have is what I call the naive autoregressive flow. And basically, instead of generating the masks, what I do is I do d minus 1 fully connected networks. So basically, for mu1, it would be randomly initialized. For mu2, I would have a network with just one input. Mu3, a network with just two inputs, and so on and so forth. So let's look at the evaluation for this naive autoregressive algorithm. So on the right, I have training data from a condition distribution. So x1 is normally distributed, x2 depends on x1. That's why the complex distribution. And if we look at the performance of algorithms like MADE, we see that they're terrible and they cannot model the density, and they also distort the latent space. And my naive autoregressive flow does slightly better, and the latent space is also not distorted. So now if we look into the problem of Monte Carlo production in high energy physics, there are certain processes that are extremely rare. And basically, if you cannot have enough statistics, you cannot build a good classifier. And I propose a solution to instead learn the density and sample from the density. And so we move on to work with the HEPMAS dataset. So the HEPMAS dataset contains features which represent momentum, energy, and other angular variables. So some of them are on the right. And in our evaluation, what we see is that the log likelihood performance is comparable. Shape analysis reveals that most of the features are very well represented, but not only do we care about the features, but also how well the correlations are modeled. So if we look into joint plots, it's kind of hard to tell. As of now, I was not able to draw any meaningful conclusions. However, there are other physics-based tests of such as the relativistic equation, which can actually help us verify the autoregressive, whether or not our autoregressive algorithm also learns the correlations. And that's my time.